Today I would like to speak to you about certain phenomena that the motion of the Earth causes during its yearly procession around the Sun. Now, as I hinted in the reading material, I am going to speak about the seasons, but I'll give you a little bit extra, and maybe you'll learn something new. So, the general outline of today's talk is going to be, I'm going to start about the seasons, then move on to the solstices and equinoxes, the apparent motion of the Sun, and if we have time, I'll tell you a bit about the zodiac, so you'll know what your sign actually means, which is nothing, by the way, but nevertheless, I'll tell you what it's supposed to mean, or at least astronomically. So, okay, the Earth is moving. We all know that. Now, two basic motions. The first one is the daily rotation around its own axis, which is the cause of which repetitive phenomenon? Yes?
Day and night.
Day and night. Brilliant. That's why we have day and night, because of the daily rotation of the Earth around its own axis. Now, there's another phenomenon, which is the yearly rotation around the Sun, and the combination of these two factors is the cause of some phenomena, and I'm going to ask the question, what kind of phenomena do these motions cause? And I'm going to start with the obvious one, maybe the one that you've heard of ever since you were in like 4th grade or something, which is the 4 seasons. Now, I didn't really have the time to edit this. I wanted to put in some Vivaldi at the moment. So, okay, first question, let's see who's done the reading. Are the seasons caused by the varying distance of our planet to the Sun? Many people believe that.
No.
No is the right answer. Yes. Yes. I'm going to go like Fox News right now and say, some people say that the seasons are caused by the varying distance of the Earth from the Sun. Well, no, they aren't. And just to prove that they aren't, I'm going to show you this mosaic. Well, it's a mosaic of 2 pictures, so it isn't really a mosaic at all. But anyway, it's 2 pictures, one stitched with the other, and I'm going to explain what you're seeing here. Actually, it's just 2 snapshots of our Sun at 2 different times of the year. Now, this was taken on January the 4th, which happens to be the time at which our Earth is at the point in its orbit, which is called perihelion. Perihelio, it's Greek, obviously. And it means that the Earth's trajectory is actually an ellipse. It's not a circle. So if it's an ellipse, it means that at some point the distance is at the minimum, and at some other point the distance is at its maximum. So actually the Earth's orbit is really like a circle. It's the deformation of the circle is very, very minute. It's very little. So it's almost like a circle, but it's not really. It's an ellipse just like any other planet. But its eccentricity is very, very small. So we got 2 points in the orbit, the perihelion, which is the point at which the Earth is closest to the Sun, and you got the aphelion in English, aphelion in Greek, which is the point that the Earth is furthest away from the Sun. Now, when I'm in your face like this, you see my figure being relatively big, whereas if I recede in the background, my figure apparently seems to grow smaller, right? Now, this is exactly what's going to happen with the Sun. When you're closest to the Sun, it's going to appear to be bigger. And when you're furthest away, it's going to appear to be smaller. So these are 2 snapshots, and as you can see, when we're closer to the Sun, it looks slightly larger than when we're furthest away. And we're closest, obviously, when it looks bigger, and that happens in January. So we're closest to the Sun in the winter and furthest away during the summer. But hey, that can't be, well, that really hits the nail concerning the previous rejection of the previous notion. But there's another thing to consider as well. This kind of thinking it's only valid for a person in the northern hemisphere. My sister is currently situated in Sydney, in Australia, and every Christmas she sends me photos of Santa in his swimming suit doing windsurf and kite surfing and all kinds of stuff. So actually, in Christmas in Australia, it's summer. It's really warm. So why should it be that the distance from the sun causes the seasons? Because it doesn't really explain that different hemispheres, opposite hemispheres, undergo opposite seasons at the same time. So that just can't be right, no matter how you look at it. So what's the real cause? Well, the real cause is this: the culprit. The culprit happens to be what is called the axial tilt of the Earth's axis. It's actually, if you imagine that the Earth rotates on a plane around the sun, and you imagine an axis which is perpendicular to that plane, well, our own axis, our axis of rotation, is not perpendicular to the plane that we're moving around the sun. It's actually tilted by around just under 23.5 degrees. And this is what causes the seasons. And I'm going to prove it to you right now. Now, let's take a look from the sun. Let's change our perspective. Let's change our reference point. If we look at the Earth from the sun as it moves around us, what we're going to see is this. At one point, we're going to see the Earth being tilted like that. At another, the axis is going to look like it's turned, and the northern hemisphere is pointing towards the sun. At another point, it's going to be the opposite of the first picture, and at yet another point, it's going to be the opposite of the second picture. Now, what this means is, as the Earth rotates around the sun, the axis actually remains fixed. So, let's just say that if I were to move around you guys, and right now you're seeing the first picture, this is the axis of the Earth. If you guys were the sun, as I'm starting to move around you during my yearly rotation, right now the axis is pointing towards you, whereas previously it didn't point towards you at all. Both ends of the axis were at an equal distance from you guys, whereas now the top end of the axis is actually closer. If I move towards the back of the room, you're going to see the third picture. If I could move through the wall, you would see the final picture, and then again the first picture. So it's like if I were holding a broomstick, which was the axis of the Earth, and I were to move around you guys, the direction of the broomstick would not change. And this is what actually causes the seasons. So let me explain what you're seeing here. At each snapshot corresponds to one of those images. Now, let's see. This one, let's start from here. Over here, which of the four pictures would you say corresponds to this stage? The northern axis is pointed slightly towards us, so it should be which one if you start counting from left to right? The second one. Yeah, that's right. So this one corresponds here. This one corresponds to which one? Well, let's imagine that we're looking from the sun, so this should be towards the left. So we're actually over here. Then moving on, it's the southern hemisphere that's pointed slightly towards us, so it's the last one, and then again over here it's the first one. So this is what actually happens during the yearly rotation of the Earth around the sun. Now, why should this cause seasons? Okay, fine, but why the seasons? Well, Actually, if we consider the way that the sunlight is distributed among the two hemispheres, when the Earth's axis is actually neither tilted towards the sun or away from the sun, and it's fixed like this, it's one of those two cases, and these happen around September the 22nd and March the 21st. This is actually where we are right now, just a few days after March 21st. So sunlight from the sun is roughly equally distributed among the two hemispheres. Whereas during the summer solstice around June 21st, the northern hemisphere is slightly pointed towards the sun, so the northern hemisphere actually has a much larger share of sunlight than the northern hemisphere, right? So that makes sense. And during the winter solstice, around December the 22nd, just before Christmas, it's the opposite, right? And just a minor trivia. Why do you think we celebrate Christmas around December the 22nd? If you actually read the Gospel of Luke, it mentions that when Christ was born, the shepherds were outside with their sheep, and I haven't seen a shepherd on December being outside with the sheep, which means that Christ wasn't actually born in the winter. He was born in the spring. And just count the months between the 25th of December and Evangelismos Theotokos. Duh, it's 9. Yeah, so when Christianity became the official religion of the Roman Empire, it needed to displace the previous festivals. And the greatest festival, one of the greatest festivals in Roman times, was the celebration of the summer solstice, the winter solstice, because it celebrated the return of the sun, and you're going to see what I'm talking about further away in the talk. The sun god, it's not just in Egypt, different variations of the sun god existed in Greece. Who was the sun god in Greece? Come on.
The guy with the 2 horses.
Yeah, 2 horses in Greece, 4 horses in India. Which is the sun god in Greece? Come on. Apollo, guys. Come on, it's Apollo. Anyway, there was this huge festival in Roman times, and they just needed to be over and done with the previous gods. So they selected that. In early Roman times, they didn't even celebrate birthdays. They never celebrated birthdays. This actually began around the 2nd century, and there was actually a conclave, and the Pope decreed that, hey, we should, if we're going to celebrate birthdays, we better celebrate the birthday of the Savior. So they just thought that, hey, around the winter solstice, that's a clever thought. So let's put it there. And 9 months previously, it's going to be the Evangelismos of Theotokos. So that's why they were selected. And actually, it's been recorded. The Patriarch and the Pope decided that they should celebrate the birthday of the Savior, and they just opted for just after the winter solstice. Convenient. Okay, if you don't believe me, this is a time-lapse video from a geostatic satellite. That's a kind of satellite that stays fixed over a point on the Earth. And these were taken over the course of a year, and you can see what I'm talking about, how the shade changes, how the direction of the sunlight changes. This is not because the sun is moving like this, it's just because of the direction of the Earth's axis being fixed as the Earth moves around the sun.
How is it possible to have it fixed, the satellite? I mean,
it just moves around following the rotation of the Earth. You synchronize the rotation of the satellite with the rotation of the Earth, so it just stays fixed all the time. Most satellites are geostatic, because when I pick up my phone, I don't want my phone with the antenna trying to find where the satellite is. It needs to know where the satellite is, so it's going to send the signal straight away. Okay, so why the seasons? What happens with the seasons? Is it just because there's more sunlight in the northern hemisphere than the southern hemisphere, and that's just about it? Well, the answer is no. Some of you might have heard that the rays of the sun penetrate the atmosphere more easily when they fall perpendicular. That's kind of true, not absolutely. The truth is much more simpler. If I take a flashlight and shed a certain amount of light on a surface, if I look from the direction of the sunlight, I'm going to see something like this, right? Now, if I do the same experiment again, but this time the surface being tilted like this, what I'm going to see is this. Now, the funny thing is that it's exactly the same amount of sunlight. It's exactly the same amount of light rays in both cases. But the difference is that in the first case, they cover an area, let's call it A, whereas in the second case, they cover a much larger area. Now, if you consider the fact that the light rays carry energy, which is translated into heat, if this heat is distributed over a larger surface, it means that less heat is being absorbed per square meter, right? If I need to distribute the same amount of money to more people, each one is going to get less money, right? So it's the same with heat. So the more, and this area increases with the tilt. The greater the tilt, the greater the area. So it means that these areas actually undergo an increase on their temperature, which is less than these areas. And how is that seen? Well, let's take a look when it's summer in the northern hemisphere, right? So the areas around here, more or less, this is a vertical surface with respect to the light rays, whereas at the polar regions, the surface has a greater tilt. And that's why there are polar surfaces on the Earth, because very little heat is being transferred on these areas, so that's why they're cold. That's why they're so cold, and they're so cold all year long. Whereas, roughly, no matter how the Earth is positioned with respect to the sun, the areas which are roughly around the equator, all year long, they're more or less vertical. So they're more or less perpendicular to the light rays. So they absorb more heat, and that's why it's hot around the equator. So it just has to do with the way that heat is distributed over a surface. And that has to do with how the surface is tilted with respect to the incoming light rays. Any questions?
Even if the Earth was not tilted, still the poles would be...
Yes, yes, yes. That's right. That's correct. Okay? Right, now, I'm going to start showing you a few simulations which have been made by the University of Nebraska. These guys are amazing. They've done some really, really amazing simulations. So I'm going to start the animation, and on the left-hand side, you just see the Earth moving around the sun, and here is an observer at some latitude, and this is how that observer would see the sun rays falling on the horizon. So this point of view has the Earth's axis fixed. So it's the sun that looks as if it were doing a motion like this, whereas this image over here, it's the sun that's fixed, and it's the axis that is moving relative to the sun. So these are just different points of view of the same phenomenon. It's just like when you're on a merry-go-round, if you step on the merry-go-round, you think that you are fixed and the earth is, and the world is moving around you, whereas before the world is fixed and the merry-go-round is moving around you. So it's just the same phenomenon from different perspectives, from different points of view, from different reference frames, to put it in terms of physics. So if the axis is fixed, then it's the sun that looks like it's moving like this. It's the apparent motion of the sun. It just looks like it's doing this motion, but it isn't. Whereas this is more close to what's actually going on. It's the sun that's fixed, and it's the Earth's axis that is actually moving relative to the sun. Now, there's another cool simulation which has to do with the sunbeam spread, how the sunbeam is spread on an area. And I'm going to change it with a latitude. I can actually change on this very nice simulation. Now, if I were on the polar regions, look how distorted the sunbeam is, because the tilt is very great. So, and it gets even more distorted over time. So, it's like the heat is distributed among a larger surface, so each point gets less heat. So that's why it's very cold in the polar regions, like I said. Okay, I'm going to pause this. Any questions about this? Okay, it's good?
The fact that the trajectory of the Earth is elliptic. When we're close, shouldn't the poles be warmer?
Well, to tell you the truth, it does play a part, but it's a very minor part. It's a very minor part. It does contribute, but compared to this, it's very secondary. So, yeah. Okay, so let's move on. Right, now, in the first few seconds, this video just shows you what I've been talking about, but in the next few seconds, it's going to show you the two hemispheres of the Earth and how heat is distributed over the two hemispheres. And it's actually based on observations from the Earth. So here it is. You see, obviously, when it's bluer, it's cold, and when it's warmer, it's red. So you can see that different opposite hemispheres actually undergo different temperatures. This is an observatory. NASA actually has a very good array of satellites that actually observe climate change. And this is very, very useful. Now, another interesting video shows, this was taken 9 years ago. It shows how the ice caps in Antarctica and in the Arctic grow and recede if it's winter and if it's summer. And you can see that when the northern ice cap is at its maximum, it's the opposite about the southern ice cap and the other way around. Now I'm going to remind you something. Antarctica is actually a continent. There's ground underneath Antarctica. Whereas the Arctic is not a continent. It's just a huge block of ice. Right? So this is actually how the continent of Antarctica looks like. And when it's more freezing, when we have summer, look at the polar caps. It's almost doubled in size. And then it just recedes to the actual size of Antarctica. And then it just grows back again.
So that's natural.
It's absolutely natural. And actually, this happens in other planets as well. And it was observed for the first time by a physicist and astronomer called Christian Huygens in the 17th century. And he observed this on Mars. He observed the distribution of the ice caps on the planet Mars. How awesome is that? He was the first guy to do it.
Let's all discuss about the melting of the ice floes and the rising levels of the sea, since it happens every year.
It happens every year, but the thing is, if it were to happen between two fixed points, well, who cares? Because it's just going to happen, and we know what's going to happen. But the thing is that the maximum is increasing. which means that it actually melts more and more and more each year. So there's less ice forming each year.
Oh, but it's not restored.
It's not restored. It's a progressive phenomenon. It looks like it's progressive. Some scientists aren't actually quite certain. I'm fairly certain that climate change is actually true. And let's just hope that there's still time to... yeah, because some people say, Fox News, some people say that, yeah, that's the way journalists want to spike their, their guests. Well, what do you think? Because some people say, well, who says it? Anyway, some people say that we might be past the point of no return. We might have caused so much change that's irreversible. And that's going to suck. But we'll have to see. Right, so, okay, let's talk about another planet in the solar system, the planet Uranos. And the tilt of the planet is huge. It's 82 degrees. Now, the thing is that if you look at it, well, what do you expect about the season on the planet Uranus? Okay? Only 2 seasons, right. And the funny thing is that the period of the orbit of Uranus is 84 years. It takes 84 years for the planet to complete a circle around the sun, which means that roughly it has 40 years of summer and 40 years of winter each hemisphere. And actually, back in, I think it was around 2006, I think I've erased the dates. This used to have dates on it. And I think it was around 2006 that we were past the equinox, which means that the southern hemisphere underwent a change of weather, and you had great disturbances in the atmosphere of the planet because suddenly you had regions that it used to be really cold, and suddenly they just receive all this heat. So this causes weather. And what I've just shown you actually has a great effect on the wind currents and the temperature of the wind on the Earth. The prime cause of weather is heat from the sun. That's it. So there we have it. Now, the other extreme case is the planet Jupiter. Planet Jupiter, or Dias, has just a very minor tilt, just almost 0, just 3 degrees. So, since it has practically no axial tilt, it means that the distribution of the light rays during its own year virtually doesn't change. So it doesn't undergo any seasons. Jupiter, there are no seasons on Jupiter. On Uranus, there are extreme seasons. On Jupiter, there are no seasons. And on planets that have an axial tilt, which is roughly in between, like Earth and Mars, you have seasons. Now, what kind of phenomena are related to the motion of the Earth? Well, the first one, and the really obvious one to us all, is the duration of daylight. Now, remember this Sunday, you need to change your watches. You need to change the time and move it forward an hour. This happens because it's called daylight saving time. It's a remnant from where most of the community used to work in agriculture. And they wanted to have as much as daylight during the working hours as they could. So they just changed the time so they could have more daylight around the usual around the usual time span. So in the summer we know that days are longer, and in the winter days are shorter. And I can tell you, when I was in London, I had these wonderful afternoons during the summer with a bit of with a drinky, as the Brits say, and we had sunset around 11. It was brilliant, really nice, really nice. And I can tell you another story because a cousin of mine studied in Edinburgh, and his fiancée she was a night owl. A night owl. She just studied night owl. She slept during the day and she studied during the night. She was that kind of person. Gosh, I don't know how they do it. Come 10 o'clock, my eyelids are just, they weigh like 1,000 tons. I'd rather wake up at 4 a.m. and study than stay up all night. Well, for some people, it's the other way around. So my cousin's fiancé used to be like that, and living in Edinburgh, in the winter, there were roughly like just over 3 hours of sunlight in the winter. And she slept during that time. So during her examinations period, for 3 weeks, she spent them as night. She didn't see the sun for 3 weeks because she was sleeping during the few precious hours of daylight. So that happens when you go in Edinburgh. When you go the further north that you go, the more prominent that this phenomenon is. So yes, we know that there are regions with, like I said right now, with little daylight and really long nights. And you might have heard that in the polar regions, daytime may last for up to 6 months, followed by an equal night. Now, all these questions really need an answer, and I'll try to give you an answer right now. Before I give you an answer, I'm going to show you that I can almost bet that none of you have ever actually observed. During the year, the actual point on the horizon where the sun rises and sets actually changes. It's not fixed. It has 2 points, 2 extreme points, and a middle point. And I dare you to take a photo, just mark 4 days on the calendar, which are roughly 3 months apart, and just take shots of the sun, and you're going to see that at sunset, and you're going to see that the sun is actually moving during the year. And this is very closely related, as I'm going to show you, with the fact that the amount of daylight changes over the course of the year. This one was taken by a Greek astronomer. He's really nice, and he has these nice pictures. This was taken outside his village. I don't remember where it is. I think it's somewhere in the Peloponnese. Another thing that changes is the zenith of the sun. Now, zenith is just the highest point in the trajectory of the sun on the sky, and it also changes. And in the winter, the trajectory is actually closer to the horizon, whereas in the summer, it's actually higher up. And that's why they say that the shadows grow longer in the winter. Shadows grow longer in the winter because it's just that the sun is lower in the horizon. If I take a flashlight and I point it towards you, and I'm pointing the flashlight roughly from the same height, then your shadow is going to be longer than when I point it like this, right? So yeah, shadows actually are longer in the winter. Another thing is that the constellations which form the backdrop against which sunrise happens on a specific day changes, and this is how your sign is actually determined. Your sign, το ζώδιό σας, is just the constellation that served as the backdrop at sunrise on your birthday. That's how your sign is determined. Now, don't get me started about signs, but nevertheless, that's how it's supposed to happen. And the specific figure is supposed to influence what happens in your life. If you're going to be wealthy, if you're going to marry the right person. There's a nice joke that someone told me, and since this is an English class, I'm going to share it with you, how to explain the difference in English between the words complete and finish. if you marry the right woman, you are complete. If you marry the wrong woman, you're finished. And if the wrong woman catches you, if the right woman catches you with the wrong woman, you're completely finished. Anyway. Okay, so in order to explain what's going on, I'm going to need to introduce briefly the concept of the celestial sphere. Now, if you go outside on a clear night and look at the sky, doesn't it feel like you're beneath a dome of some kind? Right? No? Between a dome, San Atholo. Yeah, it looks like this. And this video, which was made by an excellent astronomer from the Planetarium of Milan, is going to show us how the celestial sphere, the illusion of the celestial sphere happens. Now, in reality, obviously, stars are distributed randomly in space. But if you look from a specific point, like we do, from the Earth, it sort of looks like every star were fixed on a sort of celestial sphere. Just like that. In reality, these points are just projections of the actual positions of the stars in space on an imaginary sphere. We just project them on an imaginary sphere. And we can actually give coordinates to this sphere just like we give coordinates on the Earth, geographical coordinates. So just like we have coordinates on the Earth, longitude and latitude, we actually have celestial coordinates. And this is called the celestial equator. And it's just the projection of the Earth's equator on the celestial sphere. And I can also have meridians, just like on Earth. And I can also have the prime meridian, which happens to be the projection of the prime meridian on the Earth. And so I just project what's going on Earth on the celestial sphere. So actually, every star has coordinates. And nowadays, telescopes, which are really automated, you just give the coordinates and they just point towards the right star. So, and this fancy telescope just came out, and it just, you turn it on, and it takes 3 snapshots randomly from the heavens, and it calculates and determines on its own your geographical location. So it's like you really don't need to do anything. It's like the doofus astronomer. You just turn it on and everything is ready. Okay, so let's have a better look. Yes?
The reason why we have the impression of the dome is because of limitations in our perception.
It's just how I really... It's probably a geometrical effect. I don't know. I really can't explain right now. Just, yeah, I don't have a handy explanation why it looks like it, but it does. So, okay, let me show you quickly just a few more simulations. This is how, like I said, the position of the sun on the horizon at sunrise changes during the year. So on the solstices, it reaches the extreme points, and on the equinoxes, it just reaches the middle point. This is a very nice animation. You might have seen it in the movies. In the control room of missions in space, they actually have one of these because they really need to see what time it's going to be and how much light they're going to have when the satellite or when the astronauts return on the Earth. So I'm going to start the animation. I'm going to show you how during the course of the year the distribution of the sunlight changes. So this is how the distribution changes, and you can see that for many months the North Pole actually doesn't have any sunlight, and then it has for 6 months, and then it's the turn of the North Pole. So you can see that the distribution, like I said, changes over the months. And still I owe you an explanation, and this is how I'm going to give it to you. Let me just zoom out a bit, because this is a really, really amazing animation. Okay, so this is, I want you to imagine that this plane, this green plane, is just the horizon. And there's a guy standing at some point on the Earth. I've roughly placed it around the latitude of Athens, which is just under 40 degrees. We're 39.7 in Athens. And so this is the horizon in Athens. And during the course of the day, what happens is that the sun, what happens is that the sun appears to undergo a motion on the celestial sphere. So roughly around the east, it rises, it follows this trajectory, it sets, and then it's hidden underneath the horizon, and so on and so forth. Now, okay, this is fairly obvious, you're going to say, but what's not fairly obvious is this. I want you now to remember that video from the geostatic satellite, how it seemed that the sun were moving over and below the horizon during the course of the year, right? So if that's true, then this trajectory over the course of the year needs to change. And actually, it does. And I'm going to change the step of the animation. It's going to proceed on a daily basis. So you're going to see during the course of the year how this trajectory changes. And the trajectory of the sun actually does this over the course of the year. And now this explains why the points on the horizon where the sun sets and the sun rises actually change. This is the point where the sun rises toward the east, and you can see that it changes. And this is the point where the sun sets, and you can see that it also changes during the course of the year. Now, what about the duration of the day? Well, let me just pause this for a minute. What month is it? It's May. Let's let it proceed a bit. It's going to go slightly higher. Okay. Now, in the summer, you can see that this circle, most of it is above the horizon. Most of the circle is above the horizon, which means that the sun has to cover a greater distance over the horizon. And that's why there's more daylight during the summer. The distance that the sun needs to cover before it sets is just greater. Whereas in the winter, most of the circle is beneath the horizon. And that's why there's much less daylight in the winter. Now, during the solstices, it's the time, they say that it's the time of the longest day and the longest night. So for the northern hemisphere, the summer solstice is the longest day, and in the winter solstice, it's the longest night. And that's why in Roman times, they celebrated the winter solstice so much. Because they thought that they needed to pray in order for the sun to return. And that's what it means for the sun to return. More sunlight, good weather, right? If you're in a toga, I'd rather if it were in the summer than in the winter. Okay. Now, what's really interesting is what's going to happen if I change my latitude. And I'm going to show you what's going to happen if someone were on the North Pole. So this is how the axis, this is the horizon now. The horizon and the Earth's axis, if I'm standing on the North Pole, I could be hugging the Earth's axis, right? So the Earth's axis is right above me. And here's how the trajectory changes over time. Now, for all these months, the sun is just doing circles right above my head. So it's always day, it never sets. That's why it's 6 months daytime. It just never sets. It's just doing circles daily on that yellow circle. Now it sets, and then it just disappears for 6 months under the horizon, where it just does its thing, but it does it under the horizon, so there's no day. And I wonder, if you really like sunsets, you're going to have a really long sunset, roughly at that time. It's going to last for hours. So if you're really romantic, you should go to the poles at those specific dates. Okay. So are there any questions so far? I really like this animation. It really sheds some light on the situation. Any questions so far? You're eager to hear about the signs of the zodiac, aren't you? That's why you don't have any questions. Yes?
To understand, we have summer when we are closer to the sun.
No, it doesn't really play a part. The northern hemisphere has summer just because the Earth's axis is tilted towards the sun at that time period.
So it depends on the tilt of the eye.
Yes, that's it. Not exactly on the tilt. The tilt is all year long. It's just 23.5 degrees. But like I said, the direction relative to the sun changes. So when I'm pointing towards you with a fixed tilt of 23.5 degrees, then it's summer for this hemisphere. Whereas when I'm pointing away from you, then it's summer for this hemisphere and winter for this hemisphere. And in the transitional periods, well, it's a mixed situation. You either have autumn or you have spring right now, where in the daylight, you just want to throw your jacket away, and when the sun goes down, you wish you hadn't left your jacket at home. Okay, so I'm just going to show you a time lapse. This is taken at these pictures are taken at the University of Nebraska at the Memorial Plaza, and I'm just going to show you how the seasons change in conjunction with the trajectory of the sun. So now we're in the summer. Why is it stopping? It shouldn't stop. So now, roughly, we got the equinox. So it's the autumn equinox. These trees are going to grow yellow and orange any minute now. Yeah, well, they really, yeah, that went fast. So, anyway. I must be running low in memory or something. Yeah, probably that's what's happening. Ah, here it is. It's running more smoothly. Yeah. No, it isn't. Okay. Anyway, I think I've covered most of what I want to say. So, yes. I'm just going to show you another picture before I move on to the zodiac. Just 5 minutes more. This picture was actually taken, this crazy guy, he took a webcam and he put it in a can of soda so he could protect it from the elements, and he just placed it on the North Pole. And he took a snapshot of the sun's trajectory on some days, and he just superimposed these pictures. And you can see how the trajectory really does change over time. And the maximum height of the sun changes, and then it goes down. This is actually during the summer, because in the winter, there is no sun. Yeah.
Is it on a daily basis? No.
No. It might be on a weekly basis, on a 10-day basis, bi-weekly. Who knows? Yeah. Really nice, really nice. Well, it's slightly deformed because of the camera, but yeah, it shows you what's actually going on. Okay, you guys. The zodiac. What is this zodiac? Well, now some of you, the zodiac freaks, might recognize these constellations. Oh, gee, that's my sign. So what's going on is that as the Earth rotates around the Sun, the apparent position of the Sun changes, and it's followed by this, these points here. So this is actually where, this marks the point where the Sun would rise on that day. And you can see that we're just looking from the Earth, and we're projecting the Sun on the celestial sphere. And this changes over time. And this is how you are supposed to, what's supposed to determine your sign. Now, I really have to say this. The constellations, I'll just tell you two things. Well, supposedly, we've divided the zodiac in 12 equal parts, right? Right. Well, the constellations aren't really equal. Some of them are huge, and some of them are small. So this distribution is actually purely fictional. And in fact, if you wanted to really determine the limits of each constellation, it turns out that for 80% of the people, their actual sign is different than the one that they've been assigned. So if you wanted to take it at face value, your sign, you have an 80% chance that your sign is not actually the one that you thought. And don't you dare think, oh yes, I always thought that it never described my character. Yeah, don't you dare do that. And the other thing that I want to tell you about constellations, so I can try and wreck any belief that you might have about them, is that in reality, like I said, the images that you see of the constellations, they're just projections of the real positions of the stars. So from another vantage point, from another solar system, the constellation of Leo might look like a banana. So they're going to call it the constellation of the banana. And no wonder that I'm nuts, because I was born at that period. So really, really please, if you ever spend a cent on phoning these guys, which are absolutely phonies, please stop doing it. And just one final sentence. This is what really happens, but when someone casts a horoscope, in order to determine the light rays, the way that the light rays reach the Earth, they still use the geocentric system. So they're like totally wrong. They still calculate as if the Earth was on the center of the solar system. So please, 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 stop doing it if you're doing it. And I'm going to leave you with that. And thank you very much.